Transport Phenomena in Biosystem, Module 9, Thermal Conductivity and Mechanisms of Energy Transport, Segment 4, Effective Thermal Conductivity of Composite Solids. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about Fourier's law of heat conduction, heat conductivity, and thermal conductivity of solids. In this segment, we will discuss about effective thermal conductivity of composite solids. Thermal conductivity of two-phase solid involves one solid phase dispersed in a second solid phase, or solids containing pores such as granular materials, sintered metals, and plastic forms. For steady conduction, these materials can be regarded as homogeneous materials with an effective thermal conductivity. The temperature and heat flux components are reinterpreted as the analogous quantities average of a volume that is large with respect to the scale of the heterogeneity, but small with respect to the overall dimensions of the heat conduction system. The first major contribution to the estimation of the conductivity of heterogeneous solids was by Maxwell. Maxwell considered a material made of spheres of thermal conductivity K1 embedded in a continuous solid phase with the thermal conductivity K0. The volume fraction of embedded spheres is taken to be sufficiently small that the spheres do not interact thermally, so that one needs to consider only the thermal conduction in a large medium containing only one embedded sphere. Maxwell showed that for the effective thermal conductivity for small volume fraction can be expressed by equation 911. For large volume fraction, the thermal conductivity of the composite is given by equation 912 as proposed by Rayleigh. For square areas of long cylinders parallel to the z-axis, Rayleigh showed that the thermal conductivity tensor are given by equation 913 and 914. That is, the composite solid containing aligned embedded cylinders is anisotropic. The effective thermal conductivity for simple unconsolidated granular beds can be calculated by using equation 915 and equation 916. The G are shape factors for the granules of the medium, and they must satisfy the conditions G1 plus G2 plus G3 equals to 1, and for spheres G1 equals to G2 equals to G3 equals to 1 per 3. For solids containing gas pockets, thermal radiation may be important. The special case of parallel planar fissures perpendicular to the direction of heat conduction is particularly important for high temperature insulation, and the effective thermal diffusivity can be expressed by equation 917. For gas-filled granular beds, a different type of complication arises. Since the thermal conductivities of gases are much lower than those of solids, most of the gas phase heat conduction is concentrated near the points of contact of adjacent solid particles. As a result, the distance over which the heat is conducted through the gas may approach the mean free path of the gas molecules. Very effective insulators can thus be prepared from partially evacuated beds of fine powders. Cylindrical ducts filled with granular materials through which a fluid is flowing in the z direction are of considerable importance in separation processes and chemical reactors. In such systems, the effective thermal conductivities in the radial and axial directions are quite different and are designated by K effective RR and K effective ZZ. Conduction, convection, and radiation all contribute to the flow of heat through the porous medium. For highly turbulent flow, the energy is transported primarily by the tortuous flow of the fluid in the interstices of the granular materials. This gives rise to a highly anisotropic thermal conductivity. For a bed of uniform spheres, The radial and axial components can be approximated by equation 9.18 and equation 9.19. These simplified relations hold for Reynolds number greater than 200. For the next segment, we will discuss about convective transport of energy. Until then, I am Yusuf from Institut Teknologi Bandung.